Hello everybody and welcome to this new Trail Live episode. My name is Philippe Ozil. I'm a developer evangelist at Salesforce, and today I'm going to be talking to you about asynchronous JavaScript, and we're going to see some of the key concepts that are part of asynchronous JavaScript, along with a few other things. Before I start the presentation, I need to give you the forward-looking statement. We are a publicly traded company, so please make your purchasing decisions based on what is commercially available in the product. We're not going to talk so much about the product. There will be a section on Lightning Web Components, so bear in mind that as we go forward. So here is our agenda for today. We're going to start at a very high level, a brief refresher on what is synchronous and what is asynchronous execution, and that is not necessarily tied to JavaScript. And then we're going to go deep dive into asynchronous JavaScript. We're going to see the three different techniques that allow us to do synchronous JavaScript, and we'll finish with a section dedicated to Lightning Web Components and asynchronous code, and we're going to see some patterns on how to best handle synchronicity in there. All right, let's start. So first, let's start with the refresher. What is synchronous execution? Well, synchronous execution means it's a chain of operations that happen one after each other on a single thread. And you can see here on the slide here, I drew a thread, which is essentially this gray line with the arrow, and we can see a succession of different tasks. And one of them is a long-running task. The idea is that each of these tasks happen one after each other, and they run synchronously. They are blocking operations. And generally, when you run JavaScript is run in a single thread. I put a little asterisk here because there's an exception to that, which is pretty recent actually. We now have access to web workers, which basically allow us to do a second thread to run some operations in the background. Now, the reason why I don't want to talk too much about this is the fact that when you'll be building Lightning Web Components on Salesforce platform, you will not have access to web workers yet. This is essentially because it is not supported by all web browsers yet. So forget about it for now. It will come back on the scene later when all browsers support it. But let's just assume for now that everything we do in JavaScript is single-threaded, and the main consequence of that is that long-running operations are blocking. So you can see here on the little diagram I drew, there's this dark blue rectangle here which represents a long-running task, and that means that all the other operations that are happening after that are going to be waiting for this first task to execute, and this is part of what's causing some issues sometimes with synchronous execution. So to compensate for that, software engineers invented something called synchronous execution. And this allows us to add a bit more pseudo-parallel execution behavior. And the idea is to avoid blocking operations and moving long-running operations in the background. And the way JavaScript does that is by having an event queue and checking the status of this queue regularly when it interacts with long-running operations. A good example of that is, for example, when you have a network request. So let's assume, for example, that you have to load a bit of JavaScript from another server. And if you look at the diagram I drew here again, you can see the difference with the previous slide. We now have a separate fork and a separate path to perform the long-running operation. So this could be, for example, loading a bit of JavaScript from another website. And the reason why it's a good idea to put that in the background is that it's not efficient in terms of CPU to wait for the resource to be loaded. If I take my example of the network request to load some JavaScript, a lot of time we'll be waiting for the actual server response, and there's no point in making the CPU dedicated to that task. It can check for the result later on. So the idea is that we're going to be running some operations in the meantime and check the result of this request, and then merge back in the main branch once we have loaded our external JavaScript. And it turns out, in fact, that this pattern is pretty common. There are a lot of web APIs that rely on this asynchronous execution pattern. So again, loading resources, performing operations that rely on the browser APIs. This kind of stuff is generally run asynchronously. Let's see now how all of this translates in terms of JavaScript. So we're going to look at the different options that let you run asynchronous JavaScript. There are 3 different ways to do that in JavaScript, and they were introduced at different times. Let's start first with the oldest one. The oldest one is called Callbacks. This is the first architecture to do asynchronous code. We'll talk after about promises, which is a bit more recent, and promises are still really relevant because this is the most flexible approach for doing asynchronous JavaScript. And we'll talk about this quite recent introduction of async await pattern, which is basically promises but in a more syntactically light approach. So a bit less capabilities than promises, but some really good improvements in terms of syntax because it's a shorter way of writing things. So let's go and take a look at these 3 different technologies and actually patterns with some code samples. So we're going to be starting with callbacks. For this example, I've taken the use of the set timeout function. So this is something that is native to JavaScript, and the idea here is to wait for a given amount of time and to execute an action. The examples I'm going to use for the 3 different technologies, callback, promises, and async await, are all based on a handler for a click on a button. So we enter our code by going through the handle button click with callback function. We call set timeout, and set timeout has 2 parameters. The first parameter is a callback function. Here I have named it callback, but I could name it whatever I want. And I'm passing a reference to this function, which is defined later on in my code. And I'm then passing a second parameter, which is the duration of the timeout. So how much time I'm waiting before calling my callback. The timer here is expressed in milliseconds, so we're basically waiting a second by 1000 milliseconds. And then we do some logging. So what happens if we look at this code is that when we click on the button, we instantly write this appears instantaneously, and then only a second later we'll write this appears later. And this is due to the fact that callback function is called only after a second. It's not immediately called because of the asynchronicity of the set timeout function. So that's the purpose of callbacks. I'm sharing that with you because it's still widely used in the web APIs that are native to the browsers. But nowadays, if you're writing custom code, you generally want to avoid callbacks because it's getting to something called the callback hell, and it's a very heavy syntax. When you have a lot of callbacks, it can be very hard to read, and we have way better approaches with promises and async await to handle the same use cases and even more. So keep in mind how callbacks work, but this is not something you should write yourself when you can. Let's now talk about promises. So promises is something you'll likely have to write at some point. This is really the most flexible way to do asynchronous JavaScript. And let's take a look at an example for that. So here, instead of using the set timeout function, I've written my own long-running operation function here that is going to be called my button click handler. And I want to draw your attention to the first line in this function. This function is actually returning a promise instance. So we are calling a constructor on a promise class. And this constructor is actually everything that is returned here. So from this first parenthesis here to the one here, this is just the constructor with some arguments. The promise takes one argument here, and it's a function. This function has 2 parameters, resolve and reject. These are 2 pointers to functions that are part of the promise object. And you notice here I've used the arrow syntax here. So this is the function parameters, and this with the curly brackets here and here is the function body. Let's take a look at what this function does. So here I haven't done anything fancy, it's just for the sake of the example. Instead of the comment, I should be doing something that takes some time, so complex processing or loading some resources, whatever it is, doesn't matter. Here I'm just going to assume that this is something that works, so I've written a constant to specify the behavior of the exit behavior of the operation. You could toggle this if you wanted to copy this code and try it out. And the idea is, depending on the output, we'll be calling one of the two functions that were passed as a reference. Here, because we specified that it works, we're going to call the resolve function, and it's going to mark the promise as successful. We could also reject it if something went wrong, and that's a way to throw an error in the caller. Now, in the example code I have here, I'm not returning any particular result, but bear in mind that resolve and reject can all have various parameter values. It could output a string, an object, whatever you want for both. So you're totally free to use whatever output there. Now let's take a look at the button click handler that calls the long-running operation. So what the handler does is that it calls the function long-running operation, which is returning the promise, and then it's using the then keyword here to chain some action after the promise. By using then, we are waiting for the promise to resolve, and then we execute what's declared in the then part. Now, the then part is actually a function. Here I'm also using the arrow notation, and you can see here this is a function with no parameters, and all this does is simply log a line of text here. I also have later on the catch here, which is a function with just one parameter, which is an error. And the error is just being logged here with a console error statement. Now, the two functions here, the one that is in then and the one that is in error here, in catch, sorry, are actually the result of what is being passed to resolve or reject. So in reject, it's a string, and in resolve, there's no value here. But if we were to return a value from the long-running operation, we would pass it in the resolve function here, and we would be able to catch it there in the then function parameter. And after that, we write a line of text. So what happens there in that particular case is that when you click the button handler, it immediately displays this appear instantaneously, and it then writes this appears later. So we do have an asynchronous behavior. Of course, it's not as long as the set timeout because the long-running operation in practice doesn't do much here, but that's the idea. So that's for promises. This is really the most powerful tool you have to run asynchronous operations, and we're just scratching the surface with that. But what is very convenient with promises, and you have to remember, is the combination of then calls, because you can have one or several operations that are chained together with .then callers. Now, there's another way, which is a bit more recent in JavaScript, to do a similar thing called async await. And this is essentially a new syntax to call promises. So in the next example, we have the same long-running operation, which returns a promise here. Nothing changed here. It's exactly the same. And what is very different here is the way we're calling it. And notice here how we have an async function. So we added a keyword in front of the function here, and we added also another keyword in front of the promise returning function here. So by having an await in front of something that returns a promise, we're transforming that into a blocking operation. So the code will not proceed. We will wait for this promise to resolve before moving forward. Now, this syntax also supports return parameters. So we could have const result equals await long-running operation if we wanted to capture the return value in resolve of the promise and execute something later on. And notice also that the try-catch syntax is a bit different from the syntax for handling errors with promises, but it's essentially the same thing. We can also log errors this way. One thing that is critical to remember when using async await is that if you want to use await, you have to be in an async function. So you have to add this keyword here, async, in the calling function somewhere on top. That is critical. Otherwise, you'll get an error and it won't work. So that's it. These are the 3 ways to call synchronous JavaScript, asynchronous code in JavaScript. Let's now take a look at how we can do that in Lightning Web Components with some other examples. And before I do that, I want to just summarize a bit what are the different ways we can call asynchronous code in Lightning Web Components. So here I've listed the most common ways to have asynchronous code. The first one is pretty obvious. It's each time you click on a button or you do some action that is being triggered by the template or an event, you have handlers, you have listeners basically. So this is part of asynchronous behavior. You don't control this event yourself. It's maybe passed by a child component, by the end user or something else. And this is entering asynchronous behavior. Now, another way that is more programmatically controlled is to have Apex calls. So each time you call the backend, the server, whether it is with a wire or with an imperative statement, you're entering the world of asynchronous behavior. Same thing if you have to load resources, whether it is CSS or JavaScript, you use the platform resource loader, which is also using the network, and we use two methods for that, load script or load style, to call resources from the platform. But not only that, there are also a bunch of services that allow you to have that require actually some network operations or long-running operations. The first one, for example, is EMP API. This is the API that actually lets you subscribe to platform events or change and capture events. And the message service is the Lightning messaging service, which allows you to send or receive Lightning messages. Finally, it's also part of the native JavaScript features. You can just also call third-party services or servers by using fetch or the traditional HTML, HTTP requests. So these are relying on network, so these incur some latency and wait time. So we're going with asynchronous behavior there to avoid waiting and blocking operations. Let's take a look at some basic examples. So before we go really deep down into Lightning Web Components, I just want to show you again a couple of examples which are more tied to JavaScript. And we saw a mix of async await and promise patterns. Here I want to go into more advanced patterns. I'm going to show you 3 different examples here, and they all rely on the same task function here. This is something quite simple. We're using set timeout at the core of it to make the function wait. And the function has a name and a duration. And so essentially what it does is that it creates a promise with only a resolve pointer. It will wait for a given amount of time, and then it will call the resolve function when the task duration is over. And it will write task whatever is complete. So that's the function we're going to use, and I want to show you how you can use this function in 3 different calls with async await and promises. So the first one that we'll need to use is the sequential behavior, sequential promises. And this is how you can chain multiple promises. Here I've created 3 tasks and they each have a different duration. So what is interesting in that particular case is that I've made sure that the 3 tasks have different durations and that the task one is not necessarily the shortest one, it's actually the longest one. So this is pretty simple. What will happen is that it's going to run task 1 for 1.5 seconds, then run task 2 for half a second, and then run task 3 for a second, and then it will write all done. Pretty simple to understand. Now this is the first syntax with promise chaining, and you can do exactly the same thing with this other syntax here with async await. This is the exact same code with the new syntax. We pay attention to the async here on the top function, and then the await to execute all the tasks in the right order, 1, 2, 3. Now what is more interesting is the pseudo-parallel execution. That's the third and final example I want to show you here on this slide. You can do this with promises. There are certain functions that allow you to run tasks in parallel, and promise.all receives an array of promises that it can execute and then return something at the end. So what we have here is a simulation of parallel processing. And instead of having task return in the same order that we declared them, we're going to have task return as they're completed. So for example, in this particular case, what we would see in terms of console output would be task 2 completed, task 3 completed, then task 1 completed, and finally all done. The then call that is chained to promise.all will only resolve when all the promises in the array are resolved themselves. So this is how you can use more advanced features from promises in async await. I wanted to show you that before going into Lightning Web Components example, because we're going to use heavily those particular expressions. So let's start with the first Lightning Web Component example. A typical scenario: you have created a component. It's a custom component, and it's going to rely on some third-party resources, and we need to load those resources before we do anything. So let's assume we have to load various resource type, a mix of JavaScript and CSS style sheet. And how do we do that? Well, here I want to give you a pattern that mixes blocking and non-blocking calls, sequential and parallel calls to optimize the resource loading part. So we're looking at the lifecycle hook of our component called connected callback. So this means that our component is connected to the DOM tree. It's being added to the DOM tree and being rendered later on. And notice that you can already declare this connected callback lifecycle hook as an async function. There's nothing that prevents you from doing that. So you just have to add this async function. Of course, you don't see that often in documentation because by default, we're just using a plain function, but you can declare it as an async function. It will work the same. Then we can use some non-blocking calls for things that are not really important for the JavaScript logic. The style sheet, for example, is a very good example. There's no need to block rendering of your component or block the JavaScript execution to wait for the style sheet to load. It can load in the background. So what happens here when you have load style being called, this is the platform resource loader function, by the way. When you call this to load a CSS resource, you're not waiting for the CSS to load. Actually, you will continue to execute your JavaScript. So this is non-blocking. The style sheet resource will load silently in the background. But then let's assume now we have also some JavaScript to load, and then you need that actually to initialize your component. What you can do here is a mix of await with a series of promises being passed in the promise.all function. So this is very interesting because what happens here is that you're simulating 3 parallel requests to load 3 different libraries, library 1, library 2, library 3 here, but you're waiting for all of these requests to be finished before moving on to the init component or the final log line here. And instead of, you could do that also with a .then at the end of promise.all, but you can also use the async behavior and await behavior to block the execution of JavaScript until promise.all has returned. That means all 3 resource loading functions have been resolved. So if you had a bit of extra JavaScript to initialize your component that required those 3 libraries to be loaded, you could then call it down there. That's the whole principle. Now, this is an interesting pattern, but it's not the only one. I want to share one last pattern with you, which is a bit more advanced. And the second pattern I'm going to share with you is using this previous pattern. Let's now take a look at handling race conditions. So what is a race condition? A race condition is something that happens when you have multiple requests running in the background and you don't know which one will happen first. So it could be request 1 is done before request 2 or vice versa. And you need to control that particular behavior. Typical scenario for that is whether you need, for example, to load multiple resources and data in parallel. And then, only then when you have loaded all of these things, can you initialize your component. So this is a bit tricky because you don't know if the data will load first or the resources will load first. And the solution to implement to handle that particular race condition is to gate your component initialization with some Boolean variables. So let's take a look at this example. This is going to be based on the function we just saw before. I'm going to use an asynchronous connected callback. This is the exact same code we had in the previous pattern, but I'm going to enrich it a bit with a few other things. And the first thing we're going to do here is add a Boolean variable called libs loaded. This is to write to notify the component that it's done loading its libraries. But this is not the only thing we need to load in this particular case. We also need to load some data in parallel, and we're going to see that just after. Now, at this point, once we have loaded the libraries, we're going to try to initialize the component. And now the logic to initialize the component is moved to a separate function. And we're going to see the logic of this particular function just after. So first, let's take a look at the data loading. So here, this is a wire called for a function called getData, which returns whatever data. It's not really important what kind of data it does. But what's interesting is that it's connected to a function called getData as well. And if data is retrieved, we have a flag here, data loaded, which indicates that we have loaded data. Now, after loading data, we will also try to call init components. So what is interesting with this particular pattern is that we are trying to call init component twice in two places. Here when we're done loading data, and here when we're done loading our resources. But of course, we only want init component to happen once. So the way we work with this init component function is that we will check for both libs to be loaded and data to be loaded. And so this way, only the second call to init component will be the one that precedes to initialize the component. And here, instead of loading component ready, we should be placing the custom initialization logic. This is how you gate the component initialization with some Boolean variables. This pattern is really important because the example I gave you is with a mix of resources and data, but you could have also multiple data calls that needs to be all finished before you initialize your component. And the technique is the same, and it can work with multiple parallel calls. This is just an example here with 2, but it can work with n other examples. So these are really 2 patterns I wanted to share with you because these are the base of asynchronous behavior for JavaScript and Lightning Web Components. So along this presentation, we saw an overview of what is asynchronous versus synchronous execution. We saw 3 different approaches to handle asynchronous JavaScript. We saw callbacks, promises, and async await. And finally, we also saw some patterns for Lightning Web Components, how you can properly load resources and how you can handle race conditions. Now, I want to remind you that the proper use of those techniques is something that will guarantee that you have fewer errors, because if you weren't paying attention with the example that deals with race condition, this could trigger errors. And will also boost performance because you're going to be maximizing your CPU execution time by placing some tasks in the background and others more blocking one. Now, before I leave you, I want to give you some resources so that you can study a bit more. A lot of the information I gathered here is based on the Mozilla Developer Network, which is some sort of standard JavaScript documentation provided by Mozilla. It's a very rich environment, and there are a lot of little tutorials and resources to learn about asynchronous JavaScript, and there are also the references for things like promises, so you can see the different promise methods. Here we only scratched the surface with promises. We saw promise.all, for example, but there are other functions that you can call to run parallel promises. Now, if you want to do some hands-on, we do have a badge on Trailhead called Modern JavaScript Development, which is a project that lets you play with a couple of features from modern JavaScript, including promises and async await. Finally, if you like to look at the source code I shared in this session, I've also shared 2 resources with you on my GitHub. The first one is Salesforce DX project, which has the components that I use to demonstrate the 2 Lightning Web Components patterns. And the second one is a GIST, which contains the JavaScript examples that I've used also in the previous sections of this presentation. With that, I'd like to thank you. Thank you for watching. I hope you learned a couple of new things here, and stay tuned for the next sessions. Thank you again. Goodbye.